Welcome back to our YouTube channel. I'm Aaron from TCR, and today we want to talk about Project Poseidon.
Hi, I'm Finn. For those who haven't already watched the TCR introduction video, here's a short recap what Project Poseidon is.
Water rockets made out of PET bottles are often used to demonstrate the basic physical principles of rockets. And of course, it's a ton of fun to launch them, but the most valuable part of the experience is actually the intuition. So when you see the corresponding formulas years later, it will make a lot of sense, because they only quantify what you already knew. We ask ourselves if you could use water rockets to learn even more about the science and engineering of modern rockets. And that's our goal with Project Poseidon, while of course keeping you up to date about the cool stuff that we learned along the way. Our long-term goal is to build an electronically controlled water rocket with a thrust vacuum control system, a telemetry radio and much more. We call it the Poseidon rocket. Yeah, it would be quite naive to just start building the Poseidon rocket, because we aren't quite sure if it's feasible with all the features we have in mind. And we are only getting started to gain the knowledge we need to engineer such an ambitious project. So we decided to build 2 Pathfinder vehicles beforehand, which should help with that. We already started testing with our first Pathfinder, the Fixed Airframe Rocket, or FAR. With FAR, we hope to develop a physical model for the thrust generated by a water rocket, depending on different variables, but more on that later. Additional components for further testing are already ordered, so stay tuned for more updates early next year. The second Pathfinder vehicle is called Gimbaled Airframe Poseidon, or GAP. With GAP, we want to test out the stability system, which one day will be a fundamental component of the Poseidon rocket. Okay, with that out of the way, let's take a look at some concepts. We will start by looking at the flight profile the Poseidon rocket should be able to complete one day. We have 3 main phases during the flight. Phase 1 is the main burn, which accelerates the rocket upwards. When the burn ends, the rocket has a vertical speed, which reduces onwards due to gravity. When the vertical speed becomes 0, the rocket reaches apogee and will begin to accelerate towards Earth. This is phase 2. Finally, the rocket enters the last phase. It's about to scrap the vertical and horizontal velocity of the rocket to have a more or less soft touchdown. The tricky part is now to design a system which is able to complete this flight profile, all while being safe, reliable, light and not unnecessarily too complex. Since this is pretty hard to achieve, our current concept is quite likely to change, especially as we got more and more test data and experience. Now, let's start with a quite general concept and refine it until we reached one which could fulfill these requirements. The most basic concept is a tank, which holds the water on the bottom and the pressurized air on top. There's an opening on the bottom of the tank where the water is pushed out. This represents the most basic water rocket, a bottle. Because this rocket is not stable on its own, we need to implement a system to stabilize the rocket during flight. In model rocketry, the most commonly used systems are fins. But orbital class rockets like the Electron don't rely on fins for stability. They mainly vector thrust to be stable, at least during powered flight. So, according to our Project Poseidon goals, we want to attempt exactly that. This is also inspired by Joe Barnard of BPS.Space, who developed such a system for model rockets with solid rocket motors. He accomplished great results. A talk he gave regarding that subject is linked down below. We are in the concept phase right now, so we haven't settled on a specific design yet. More on that in a dedicated video in the near future. Slowing down the rocket, the third part of the flight, can be done with parachutes. This is quite common in the model rocketry community because it's effective and quite simple. When you look at orbital class rockets, they either splash down in the ocean, burn up in the atmosphere, or come back to Earth in a more reusable way. But that's maybe something for later in the project.
To perform multiple controlled burns during the flight, we also need a way to control the flow of the exiting water. One concept would be to put a valve right before the nozzle. When opened, water would flow through the valve and exit the rocket. While this would be easy to build, far too less water would flow through it to produce a decent thrust to lift off. Instead, we decided to build the rocket out of 2 tanks with valves in between. The upper tank holds the pressurized air and the lower tank the water. As soon as the main valve, which connects both tanks, is opened, air from the upper tank pressurizes the lower tank and water is pushed out. The burn ends when the main valve is closed and the secondary valve depressurizes the water tank to preserve the remaining water. In theory, this would allow for much higher thrust because a compressible gas can pass through the valve much more easily than an incompressible fluid. To fuel up the rocket on the launch pad, we need a way to fill in the water and to pressurize the upper tank. If you think about it, the launch pad is a nice engineering task in itself. The rocket must be held upright and stable. We need pressurized air and water lines, which should be controllable from a distance. Right before the launch, the rocket needs to be automatically disconnected from the pad as well.
It is also important to think about burn times. A water rocket, built out of a PET bottle, usually accelerates over a very short time span and then coasts for a long time until apogee. Because we want to stabilize the rocket during the burn by vectoring the thrust, this is not an option for us. We actually need a burn time in the seconds. And this is also a nice segue to the test objectives of FAR. With the prototype FAR, we hope to find our sweet spot of thrust and stored energy depending on the tank size, air pressure, valves and the nozzle. To do that, we want to model the thrust of a water rocket using the aforementioned concept with mathematical equations and simulations. The FAR Pathfinder is built in a modular way so that we can swap out valves, change tank sizes and more. The nozzle is connected to the bottom of the lower tank by a hose. This enables us to record the thrust and mass change of the rocket independent of each other, with the data collected over multiple tests with different hardware configurations. We then try to further enhance our physical model. The requirement for the thrust is to be higher than the weight of the rocket to actually lift off. The ratio is also known as thrust to weight ratio. To reach a decent apogee height, we need to convert the stored energy of the rocket to kinetic energy over the intended burn time as efficiently as possible. As soon as the model is mature enough to be aligned with our test data, small deviations are of course expected, we will use it to simulate a lot of different rocket configurations. The one that matches our requirements the most will be used as a basis for GAP. While FAR was a cheap and quick to build prototype, GAP will use a lot of components we later want to actually fly. This includes, for example, carbon composite tanks and the TVC structure. To test the hard and software that one day will be the stability system of the Poseidon rocket, GAP will be held down in a gimbal suspension to test it safely on the ground. That's it for today's video. We hope you liked it and are open for any kind of feedback regarding the video or our plans. Next video in the Project Poseidon series will probably be about the knowledge we gained through testing with FAR, but this may change. If you want to stay up to date, consider checking out our Instagram, Twitter and website. Links to all of them are provided down below. Bye, until the next time.